Hi friends, welcome back to our YouTube channel. Today we have to discuss about IEEE 754 double precision floating point representation in computer architecture course, computer organization course, computer organization and architecture course. In the previous videos, we have already solved 4 example problems on single question format. If anybody wants, please refer the 4 example problems. Now we can go for floating point representation using IEEE 754 double precision format and its example problem. The given example problem is represent plus 116 base 10 in IEEE 754 double precision format using implicit normalization. So before solving this problem, first of all, you have to know about IEEE 754 double precision format. It contains 64 bits starting from 0 and ending with 63. Total 64 bits are there in IEEE double precision format. These 64 bits can be divided into 3 fields. The first one is mantissa field that can be denoted by M. So 52 bits are allocated for mantissa starting with 0 and ending with 51. Next, 11 bits are allocated for exponent that is denoted by capital E starting with 52 and ending with 62. Next, the third field can be called as sign bit field. Only one bit can be allocated for sign bit that is denoted by capital S starting with 62 and ending with 63. So based on the sign bit, we can say that whether the given decimal number is a positive decimal number or negative decimal number. Suppose if S value is equal to 0, we can say that the given decimal number is a positive decimal number, positive decimal floating point number. Suppose if S value is equal to 1, we can say that the given decimal number is a negative decimal floating point number. Okay, so based on the S value, we can say that whether the given decimal number is a positive or a negative number. Okay, now so the given decimal number is plus 116 base 10. Okay. Now first we can go for sign bit field. So here if the sign bit field S value is equal to 0, we can say that it is a positive decimal number. S value is equal to 1, it is a negative decimal number. Okay. So the given decimal number is plus 116 base 10. So it is a positive decimal number. So that we can say that the sign bit value can be treated as 0. So here the sign bit S value is equal to 0 because given decimal number is a positive decimal number. Okay, next, already we know the S value. S value is equal to 0. Next, second one, we have to find out the mantissa. Okay, for finding out the mantissa, first of all, we have to convert the given decimal number into binary equivalent. To convert the given decimal number into binary equivalent, we have to successively divide it with 116 with 2 until the quotient value is 0. Once the quotient value we are getting 0, we have to write the remainders from bottom to top. So now I am taking 116 successively divided with 2 until the quotient value equivalent to 0. 258 116 remainder value is 0. So quotient 58 not equal to 0. So that successively divided with 2. 2 29s 58. So remainder value is 0. Quotient 29 not equal to 0. We have to successfully divide it with 2. 2 14s 28. Remainder value 1. Quotient 14 not equal to 0. So that we have to successfully divide it with 2. Next, 2 7s 14. Remainder value is 0. So quotient 7 not equal to 0, so that we have to successively divide it with 2. 2 3s 6, remainder 1. Quotient 3 not equal to 0, successively divided with 2. 2 1s, remainder 1. Quotient 1 not equal to 0, so that we have to successively divide it with 2. 2 zeros, 0, remainder 1. Now quotient value we are getting 0, so that we have to stop successively divided with 2. So then write the remainders from bottom to top. Bottom to top. So 116 base 10. The equivalent binary number is 1. Next this one. Next this one. Next 0. Next 1. Next 0. Next 0. So 111 01 00. Okay. Next, this is base 2. So here 111 01 00. Here where is the decimal point is there? The decimal point is here. Okay. Now we have to move the decimal point to which place? For that purpose, we have to use two types of normalizations. First one is explicit normalization. Second one is implicit normalization. In the case of explicit normalization, the given formula is -1 whole power s into 0.m into 2 power e minus bias, where s is nothing but sign bit, m is nothing but mantissa, e is nothing but biased exponent, and the bias value is, here we have to find out the bias value in double precision format. The formula is 2 power n minus 1 minus 1. This is the formula for bias, where n is nothing but number of bits allocated for exponent. How many number of bits allocated for exponent? 11 bits. So that substitute 11 in the place of n. So 2 power 11 minus 1, 10. 2 power 10 minus 1, that is 2 power 10 value 1024 minus 1, that is 1023. So bias value in the case of double precision format is 1023. Okay, so this is the bias value. Next, whereas in the case of implicit normalization, the given formula is -1 whole power s into 1.m into 2 power e minus bias. Okay, only the difference between the two types of normalization is this point and this point. In the case of explicit normalization, only 0.m is there. In the case of implicit normalization, only 1.m is there. Remaining things are similar. Okay. Now, in the given problem, we are using implicit normalization, so that we have to use this formula. Among the two types of normalizations, the default one is also implicit normalization. Whether it is specified in the given problem or not, the default one is implicit normalization, so that we have to use implicit normalization. We have to use the implicit normalization. In the case of implicit normalization, the decimal point is always there after the MSB bit 1. Okay, so that we have to move the decimal point in that binary equivalent also after the MSB bit 1. Here, where is the decimal point is here? The decimal point is here after the LSB bit. Now, we have to move this decimal point from right to left after MSB bit 1. Okay, how many bits we have to move? So, from this position to this position, 1 bit we have to move. Next, from this position to this position, 2 positions we have to move. Next, this position to this position, 3 positions we have to move. This position to this positions, 4 positions we have to move. This position to this position, 5 positions we have to move. This position to this positions, 6 positions we have to move. So the decimal point is here after the MSB bit 1. So 6 positions we have to move from right to left. So that what is the result we get? That is 1.110100, that is multiplied with 2 power 6. How many number of places the decimal point can be moved from right to left? That can be multiplied with 2 power 6. So 6 positions we have to move from right to left. Okay, now, so it is in the form of 1.m into 2 power e minus bias. So see this one, in the implicit normalization, this is there. So 1.m into 2 power e minus bias. So the above number is also in the form of this one. Okay, then when we are comparing this one with this one, what is m value? M value is equal to, m value is always a fraction number, so that fraction number start with 0 point. So this is the m value, 11010. This is the m value, 0.110100. Okay, next one, third one, we have to find out the e value. Okay, to find out the e value, so now here we have to compare previously this one. Now we have to compare these two. that is 2 power e minus bias is equal to 2 power 6. Here bases are equal, then powers are also equal. So that e minus bias is equal to 6. Okay, then we already know the bias value in double precision format is 1023. So therefore E is equal to 6 plus bias. So what is the bias value? 6 plus 1023. So that is equal to 1029. Okay. Now we have to find out the binary equivalent of 1029. So 1029 can be written in the form of nearest 2 powers. So we already know that 2 power 10 value is 1024. Remaining thing is 5. 5 can be written as nearest 2 powers 2 power 2. So that is 4. 1024 plus 4, 1028. Remaining is 1. That is 2 power 1. Okay. So see this here. 2 power 10, 2 power 9, 2 power 8, 2 power 7, 2 power 6, 2 power 5, 2 power 4, 2 power 3, 2 power 2, 2 power 1, 2 power 0. What are the 2 powers we have to use here? That 2 powers at that places we have to put 1. Whatever the 2 powers are missing at that places we have to put 0. So here 2 power 10. Here we are using 2 power 10, so that put place 1. Next 2 power 2, here we have to use, in this place we have to put 1. 2 power 0, 2 power 0, here we have to use, so that we have to put 1. So remaining bits are filled with 2 power 9 missing, filled with 0. 2 power 8 missing, filled with 0. 2 power 7 missing, filled with 0. 2 power 6 missing, filled with 0. 2 power 5 missing, filled with 0. 2 power 4 missing, filled with 0. 2 power 3 missing, filled with 0. 2 power 1 missing, filled with 0. So what is the value you are getting? That is equal to 1 7 zeros 101. Here we are getting. Okay. So here 2 power 10 means 1024. 2 power 2 means 4. 2 power 0 means 1. That is equal to 1029 here. So 1024 can be written as 2 power 10. 4 can be written as 2 power 2. 1 can be written as 2 power 0. Only in these places we have to put 1. 1, 7 zeros, 1, 0, 1. Whatever the 2 powers we have to use, in that places we have to put 1. Whatever the 2 powers are missing, in that places we have to put 0. In this way, simply we have to find out the binary equivalent. This procedure you do not know, simply you have to follow this procedure. So now, what is biased exponent value you are getting? This one. Now, we know the S value, we know the M value, we know the E value. E value is 11 bit. See this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 bits we are getting. Now substitute these three values in 64-bit format. First, what is S value? S value is 0. This is 1. What is E value? E value is here. 1, 7 zeros, 1 0. That is 11 bit. Next, what is Mantissa value? Mantissa value we have to write after the decimal point, whatever it is there, that we have to write. 1, 1, 0, 1, 0, 0. How many bits are allocated for Mantissa? 52 bits. Only how many bits here is there? 2, 4, 6. So remaining 46 bits are filled with zeros at LSB side. So 52 bits total, 6 bits are there in the Mantissa after decimal point. The remaining bits are filled with zeros. So in this way, we have to solve this given problem in IEEE 754 double precision format. I hope all of you understanding this video. If you have any doubts, please put your doubts in the comment section. I will try to clarify your doubts. If you really like this video, please subscribe my YouTube channel, Divvela Srinivasarao. After subscribing my YouTube channel, click on the bell icon to get the future updates in my YouTube channel.